Hello students, today we are going to study moment of inertia. For a rigid body or system of particles, we have to study a new quantity in rotational dynamics, which is the moment of inertia. Here, before going to discuss definition, significance of moment of inertia, we have to derive one simple expression for rotational kinetic energy. Rotational kinetic energy. This we have to derive. For that, we consider a body of any shape. But here we assume that this body is consisting of n particles. There are n particles in the body. Here this body is rotating about the axis of rotation. We can here show this is a body and it is rotating about this axis of rotation like this. So this rotation is for irregular shaped body and its axis of rotation can be shown, which is perpendicular to the plane of figure. So this is the axis of rotation and the body is rotating in this way. This is the angular velocity of rotating body. It can be shown like this. The body is rotating with constant angular velocity or constant angular speed omega. Now we want to derive the relation for rotational kinetic energy. For that, we proceed by considering linear velocities of different particles in the body. So we consider here n particles having masses m1, m2, m3 up to mn. For the first particle, suppose its mass is m1, it is situated at shortest distance r1. So r1 is the distance of first particle from the axis of rotation and this distance is perpendicular distance. It is the shortest distance. Similarly, for the second particle, say m2, perpendicular distance is r2. Similarly, for the third particle of mass m3, perpendicular distance is r3. For the nth particle, which is denoted by mn, last particle, here perpendicular distance is rn. So r1, r2, r3 be the perpendicular distances from the axis of rotation. Here we denote O is the point through which the axis of rotation passes through the body, or here through this section of a body. Now for each particle we have to consider the speeds. For the first particle, linear velocity or magnitude of linear velocity is v1. For the second it is v2. For the third one is v3 and for the last particle it is vn. we know the relation between v and omega, means linear velocity and angular velocity. The relation between them is v is equal to r into omega. That can we write here for each particle. v1 is equal to r1 omega. For v2 it is r2 omega. For v3 it is r3 omega. For last particle it is rn omega. So this is the linear speed. Now easily we can write kinetic energies. Kinetic energy of the first particle, it can be written as. So before going to kinetic energy, we show here velocities like this. For the particle m1, velocity is directed along the tangent to the circular path. Here circular path is not shown, but you have to imagine for the particle having the circular path in this way, and tangent can be shown v1. For m2 it is v2. For m3 it is v3. For mn it is vn, like this. So these are the linear velocities. Now kinetic energy can be written as half mv1 square. This is kinetic energy for the first particle. It can be equal to half. Here for the first particle mass is m1. We write here half m1 v1 square. So we get half m1 into v1 square is r1 square omega square. Substituting v1 as r1 omega. So this is kinetic energy of the first particle. Similarly, kinetic energy of the second particle is half m2 r2 square omega square. We write for the third particle half m3 r3 square omega square. For the last particle, here we show here number of particles having different kinetic energies. For the nth particle it is 1/2 mn rn square omega square. So for all particles the kinetic energies are shown by our usual relation half m1 v1 half mv square. So this is the translational kinetic energy. But we have to derive rotational kinetic energy. But here the concept is rotational kinetic energy is equal to sum of translational kinetic energies. So you have to note here that sum of translational kinetic energies of all particles, all individual particles. So simple addition is there. It can be half m1 r1 square omega square plus half m2 r2 square omega square, and the sum extends up to nth particle's energy is half mn rn square omega square. Now this can be rewritten as by taking half outside the bracket, and inside the bracket we only put m1 r1 square, m and r like this, m1 r1 square plus m2 r2 square plus mnRn square and closing the bracket, multiplying it with omega square. We get the same equation here, but it is rewritten in this way. Now the next step we can take here. Rotational kinetic energy. Next step is like this: half, and bracketed quantity can be written as summation of MIRI square, where I varies from 1 to n, and multiplied by omega square. The same bracket M1 R1 square for the first term. For the second term we substitute I is equal to 2 M2 R2 square, and for the last particle it is Mn Rn square. This is the sum, and this bracket is denoted by a new letter or new quantity as I, and this I is called as moment of inertia. Here we write it like this. Here where summation of MIRI square, where I varies from 1 to n, it represents the quantity I, is called as moment of inertia of a body or of the object about given axis of rotation. About given axis of rotation. Given axis means the axis which we have considered. So is the moment of inertia of a body about given axis of rotation, means the axis we have considered. So this is the introduction of a new quantity in a derivation itself. It gives us the idea of all masses and distribution of masses from the axis of rotation. This moment of inertia, the new quantity which we have taken, it represents what it represents, or it depends on masses of all particles as well as distribution of masses about the axis of rotation. Distribution of particles or distribution of masses about the axis of rotation. So I depends on mass of each particle, like M1, M2 up to Mn. It depends on distribution, means distances from the axis of rotation, R1, R2, Rn. So this is about the new quantity. Here we have defined moment of inertia. From this relation we can define it. The mathematical equation itself means I is equal to sum of MIRI square. I varies from 1 to n. This mathematical expression defines the moment of inertia. We can define it like this. It is the sum of which quantity? Sum of the product of mass, sum of product of mass of each particle, and r square means square of the distance, and square of its distance from the axis of rotation. From the axis of rotation. So this is the simple definition. Moment of inertia is defined as the sum of products of mass of each particle and square of its distance from the axis of rotation. Now, as it is the product of mass and square of distance, here SI unit of moment of inertia you can easily write as kilogram into meter square. Kilogram meter square is the SI unit of moment of inertia. You can also write the dimensions of moment of inertia. So this is about the definition of moment of inertia. Now, as the new term appears in the discussion, we must have to write its meaning. We must have its meaning or physical significance, because this term here appeared first time in this chapter, so we must have to mean it. Mathematically we have expression, also we have stated its definition, SI unit, dimensions, all these things, but we must have to know its meaning. So for that we consider the expression for rotational kinetic energy. We have rotational kinetic energy as half into I into omega square. Similarly, we have one expression in our translational motion is translational kinetic energy. Translational kinetic energy, it can be given by half into m into v square. If m is the mass of body, v is the velocity of the body, then we can easily write translational kinetic energy or linear kinetic energy as half into m into v square. So there are now two relations. First is A, second one is B. So from this relation we can write the analogy. Analogy between translational kinetic energy and rotational kinetic energy. We here say that in sentence we say that here rotational kinetic energy is analogous to translational kinetic energy. Simple sentence we have made here. From these two equations, here on the LHS, rotational kinetic energy is there. It is analogous to translational kinetic energy. Translational kinetic energy. Now on the right hand side, here half, here v and omega. V is linear velocity. We know that linear velocity and omega both are analogous to each other. Omega is analogous to v. Here we write omega is analogous to v. Means angular velocity is analogous quantity of linear velocity. Similarly, here I is analogous to m. Means moment of inertia is analogous to mass. I is analogous to m, or moment of inertia is a quantity in rotational dynamics. It is analogous to mass that we have considered in linear or translational motion. Now what we have mean for mass? Mass is a physical quantity. It is fundamental quantity. Its meaning we have taken that it measures, it is a measure of inertia of a body. Inertia of a body. So try to understand this statement here. Mass means it is a measure of inertia of a body, or its physical significance is that it is related to inertia of the body. What you mean inertia? So for that we recall one example that we have usually taken for the understanding of the inertia. So when we travel with car takes uniform velocity, and if it suddenly stops, then we get pushed in the forward direction. This is because our body has got tendency to move in the forward direction. Our body maintains the state of forward motion. A body to maintain the state of uniform motion or uniform translational motion, or oppose the change taken by the car or the system, that is called as inertia of a body. Here I can write its significance like this. It is inertia represents tendency to oppose the change in translational motion. To oppose the change in translational motion. The change may be change in state of rest or state of uniform motion. So this is the meaning or significance of mass. Here we have taken I is analogous to m. So we have to give by analogy the physical significance of moment of inertia. Moment of inertia. Moment of inertia is denoted by I. It is similarly we write the same sentence, similar sentence here. Moment, it measures. Here first sentence we write it is a measure of rotational inertia. Not simply inertia, as it is related to rotational motion, we write its meaning simple. It is measure of rotational inertia, or it means the rotational inertia. Now what we can write for the second? In case of mass we have written inertia is the tendency to oppose the change in state of translational motion. Here we write I, or moment of inertia, represents opposition, or it is tendency to oppose, represents tendency, same sentence we write, tendency to oppose state of rotational motion. Not simply the translational motion, rotational motion. In other words, it has tendency to maintain the state of rotational motion. It represents the tendency to oppose the change of rotational motion. Change in state of rotational motion. Change in state. Here we write change, oppose the state of rotational motion like this. So this is the simple meaning of mass and moment of inertia. It is called as physical significance. So there is one short question that define moment of inertia and give its physical significance. So simple, in one sentence also we can give the physical significance that it represents tendency to oppose the state of rotational motion. A change in state, here tendency to oppose change in state of rotational motion. So this can be understood in this way. This is the physical significance of moment of inertia. Now, related to this moment of inertia, there is again one quantity, that is radius of gyration. This is also can be understood from the concept of moment of inertia. So here we have taken, for the derivation of kinetic energy, we have taken the body like this, consisting of n particles. Same body we imagine here. Here the angular velocity is omega we have taken and obtained the relation for moment of inertia. Introduced one bracketed quantity here like this, I is equal to m(i)r(I) square, where I varies from 1 to n. Is the moment of inertia. It can be obtained mathematically by this relation. Now we have to consider the same mass of a body, because mass of body here, as the particles are here having masses m1, m2, m3, if we add all these masses, then total mass of the body is m. Here suppose that these all particles are collected in a single point, or supposed to be concentrated in a single point, and that mass is denoted by m. If now this mass is revolved along about the same axis of rotation, here like this, axis of rotation is taken like this, and if it is rotated here, but the distance, the radial distance or perpendicular distance or radius of the circular path we have taken, it is denoted by k. Then by definition of moment of inertia, if we take the product of mass and square of its distance from the axis of rotation, if it is found that it is having the same value I about the axis of rotation as we have previously found I by taking the summation of product of mass of each particle and square of distance of each particle from the axis of rotation. So by definition moment of inertia is I, and by taking the whole body at a single point and calculating by taking the distance k, if moment of inertia are same, then this k is called as radius of gyration. It can be written as k square is equal to I upon m. K can be equal to under root I upon m. Now this is the expression for k, means radius of gyration. Condition here is that mass of a whole body which we have considered is supposed to be concentrated at a point which is situated at radial distance k, so as to possess the same moment of inertia as that of the body. So this can be a definition of radius of gyration. Radius of gyration is the distance between the axis of rotation and the point at which whole mass of the body is supposed to be concentrated so as to possess the same moment of inertia as that of the body. Then that particular distance, that particular radial distance is called as radius of gyration. As it represents distance, its SI unit is meter. Now, as this represents a distance, it gives the idea of distribution of mass. Distribution of mass. So, try to understand again the concept and revise the concept of moment of inertia. In moment of inertia also we have taken that I depends on m, I depends on r, means distance from the axis of rotation. So these two factors determine the moment of inertia. Here the distribution of mass we have considered in the form of distances like r1, r2, r3. Here there is only one distance we have taken, but it gives the idea of distribution of mass in the body. So if the moment of inertia, if here we write like this, if k is small, then we mean that all particles are close to the body. If k is large, the particles are away from the axis of rotation. So here I write the description like this. If k is small, we mean that particles are nearer to the axis. If k is large, we can say that here particles are farther or away from the axis. So we have to mean it like this. If for a given body, if k comes to be small, if the we here take one example that if we have a disc like this having mass m and its axis of rotation is shown like this, and for this disc, this is the first disc, suppose its radius of gyration is k1, and if there is another disc but having the same mass m, but it is another disc, suppose it is second disc, in this case the axis of rotation is also same, and but k is different. Here k is denoted by k2. As here disc is small, mass is concentrated near the axis, therefore k1 is small. In the for the second disk, K2 we have found and it is found to be large. Here K2 is greater than K1 because even if masses are same, in the first disk mass is concentrated near the axis. In the second case, mass is farther from the axis. So here distribution of mass is showing larger distances from the axis of rotation, therefore K2 is large. So here this is the physical significance of radius of gyration. So it indicates the distribution of mass from the axis of rotation. If K is small, particles are closer to the axis, and if K is large, they are farther from the axis of rotation. So this is the physical significance of this radius of gyration. Now here we have related radius of gyration to the moment of inertia of a body, and while considering the derivation of rotational kinetic energy, definition of moment of inertia, we have considered the body which is consisting of particles m1, m2, m3 up to mn. They are situated at distances. Of course, they are perpendicular distances from the axis of rotation. Like we have shown like this, m1 situated at distance r1, r2 and so on. We have taken such description. There are n particles, but practically such particles we cannot show every time or for every body, because for a rigid body there is continuous distribution of mass. Continuous distribution of mass. So we cannot here show every time m1 is the first particle, second particle like this, but the particles are closely situated. There is continuous distribution of mass. Therefore, instead of taking m1, m2, m3, mn situated at distances r1, r2, r3, rn like this, we have to show the body, the same body we have to show here, irregular body, and we can here show a small mass dm which is situated at distance, perpendicular distance r, and for that we can write the expression for moment of inertia. So here again we write our expression that we have studied, that is sum of product of mass and square of its distance, like this. Here the same meaning we have to take. Moment of inertia we have to denote by I. It is equal to, instead of summation for this such distribution, means discrete distribution, we have to replace summation by integration. This is the symbol of integration. Integration of dm. So instead of mi, means m1, m2, m3, we have to consider single particle dm and multiplied by its distance r square. So here there is one mass element dm. Actually there are number of elements. If we all add all these elements, then it gives us the total mass m. So integration is used to have the summation or total when there is continuous distribution of mass. and this we have taken for discrete distribution or simple distribution here. So integration is used instead of summation here. So here instead of m1 m2 we have dm, all these small mass elements, but in that integration we have written simple dm into r square, means mass, product of mass of one element multiplied by its square of distance from the axis of rotation. If we take the integration, then we get the same moment of inertia I. So in further discussion and further topics of rotational dynamics, instead of using this simple definition, we have to use the expression for moment of inertia as I is equal to integration of dm into r square. But for the numerical problems, we use this definition also. But for the derivations, we have to use general purpose, we use this definition. Both the definitions are one and the same. But for the sake of understanding, we have taken the distribution of particles for a rigid body. But in further topics, we use this definition. So this is about the 3 points like moment of inertia, radius of gyration and rotational kinetic energy. So today we'll stop here. Thank you.